Today we have this talk from Adrián. Adrián is a PhD student from the University of Seville, and he is working at the National Accelerator Center located in Sevilla, CNA, and he specialized in the study of the IBIC techniques. IBIC is an ion beam accelerator, but in this case it's used for testing semiconductor devices. And I understand that he will talk about these techniques that he's working on the last years. So he's visiting us at CNM during this last month. And well, we are collaborating in a project. It's called GRACE. This is a project to study silicon carbide, to fabricate and study silicon carbide detector for Archaeometry environment. So Adrián, please go on.
Thank you.
Thank you for visiting us.
Thank you. Thank you for the introduction. And as he said, I'm a PhD student at the Centro Nacional de Aceleradores, CNA in Seville, Spain. In this talk, I will give an overview of the CNA, commenting on the facilities as well as the research being carried out and the service provided. Next slide. Okay. Where is the CNA? Well, it's located in the Cartuja 93 Science and Technology Park on the Isla de la Cartuja in Seville, Spain. Here is the facade, and the area is full of universities, companies, and well, maybe some of you may know this place because of the Universal Exhibition held in Seville in 1992. Since it was first put into operation in 1998, the CNA has had as its mission the development of research in particle accelerators and their multiple applications. The CNA, recognized as a singular scientific technical facility, is an open center so that the national and international scientific and technological community can carry out research using its facilities. It's a joint center of the University of Seville, the Andalusian Regional Government, Junta de Andalucía, and the Spanish National Research Council, or CSIC. The CNA has a set of particle accelerators that makes it a unique center in Spain, both in terms of its facilities and the different tasks it performs. These are the main facilities. We have a 3 megavolts Van de Graaff type tandem accelerator, 18 or 9 MeV cyclotron accelerator, a 1 megavolt Cockcroft-Walton type tandem accelerator, an ultra-compact accelerator, MICADAS, which stands for Mini Radiocarbon Dating System, a Cobalt-60 radiator, and a PET-CT scanner. This is where I will try to explain hereafter, although I am by no means an expert in all of this technology. These are the main lines of research and services provided by the CNA. Well, I apologize in advance if I have forgotten any of them. It's very difficult to cover all the work done at the CNA, but I've tried my best to include and talk about everything a little bit. We have application of ion beam analysis, or IBA techniques, characterization of detectors and electronic devices, basic experimental nuclear physics, accelerated mass spectrometry, or AMS, archaeometry, nuclear medicine, irradiation of samples, carbon-14 dating, research on nuclear fusion, etc. The first accelerator installed was the 3 megavolt Van de Graaff type tandem accelerator. The principle of operation is as follows. Here you can see a very simple schematics of what a tandem accelerator is. It is an accelerator tank whose center is connected to a positive potential with respect to the ends, which are connected to the ground. Therefore, there is an electric field whose lines point in a straight line from the center of the tank to the ends. In our case, this potential can be up to 3 million volts, hence the name 3 megavolt tandem accelerator. And tandem comes from the fact that the charged particles are accelerated in 2 stages. So imagine if we want a charged particle to accelerate from one end of the tank towards the center, it must have a negative charge to accelerate in the opposite direction of the electric field lines. So the first thing to do is to add an extra electron to an initially neutral atom to give it a net negative charge. And it accelerates towards the center of the tank. At this point, we need the net charge of the particle to be positive. That is, we need to get rid of the electrons. This is achieved thanks to the stripper gas in the center of the tank. This gas absorbs electrons and makes the particle's net charge positive. And from here, the particle accelerates along the field lines towards the center of the, towards the end of the tank. And thus, the final energy of an ion will have this expression here, where eta is the final charge state of the ion, E is the electron charge, V is the applied voltage, and J is the injection energy. It is called a Van de Graaff type because the potential in the center of the tank is reached by transferring charge through friction with some elements that are called pellets that form a chain. This accelerator is mainly dedicated to the characterization and modification of materials using ion beam analysis techniques and ion implantation, as well as to the study and development of nuclear instrumentation, mainly radiation detectors, but any kind of electronic device actually. I won't go into too much detail, but an ion beam analysis technique is, in summary, exploiting our knowledge of the interaction of ions with matter to obtain information about the materials. We have Rutherford backscattering, particle-induced X-ray emission, etc. At the present time, the tandem accelerator has 6 available beamlines to characterize and to modify materials, as well as for nuclear physics research, and this PANOS line, which was recently installed to produce neutrons. So let's have a look to them very briefly. First, the -30 degrees line, or the nuclear physics beamline. This line develops and tests nuclear instrumentation elements like detectors, electronic devices, etc., that will later be used in international and nuclear physics facilities. This is the microbeam line, and the focusing system is manufactured by Oxford Microbeam. And with this system, it is possible to focus on the sample with a beam of a few microns. The scanning coils and the scanning mode allows elemental maps to be obtained with which give the spatial distribution of concentrations in the sample. The magnetic coils of the scanning system also allow a maximum scanning area of 2.5 by 2.5 square millimeters for 3 MeV protons. This is the line in which I mainly work, although it is not the only one. And here we carry out studies of semiconductor detectors. For example, we have characterized silicon carbide detectors and LGADs manufactured at CNM. And well, it has many advantages, such as being able to obtain spatial information, to be able to perform irradiation of specific areas in many parts of the same detector. We can rotate the sample, etc. On the 0 degrees line, we have 2 chambers. The first one, the multipurpose IBA chamber, it has a design that allows different ion beam analysis techniques to be carried out at the same time, because it has many kinds of detectors. And here we carry out experiments in basic nuclear physics, material analysis, etc. At the end of this same line, it is the ion luminescence chamber, also called TAMARA, which stands for Temperature Analysis Measurements and Radiation Applications. This chamber allows measurements and irradiations at temperatures up to 500 degrees. Well, we also use it to characterize detectors for high temperature, like the silicon carbide. The next line, this is the irradiation chamber, mainly intended for irradiation of large areas. We have also used this chamber on certain occasions to irradiate electronic devices to later study their response after a certain received dose. This is the channeling chamber for channeling, which is a IVA technique. The beam line also includes a beam profile monitor and Faraday cap. The chamber is equipped with 2 particle detectors and an X-ray detector. And the sample holder is mounted in a 4-axis microcontrol goniometer to move the sample in around whatever axis. And the external beam, this line is mainly used in art and archaeometry studies. Due to the frequent inhomogeneous nature of this kind of objects, the use of external ion beam analysis combined with a good resolution exhibits numerous advantages. With the idea of achieving good spatial resolutions, a series of elements have been purchased from Oxford Microbeams too, including a precision for jaw object slit and an exit nozzle set with micrometer adjustment. And finally, the most recent one, a few years ago, the CNA developed the first accelerator-based neutron facility in Spain. It's called Hispanos. Stands for Hispalis Neutron Source. Low energy proton or deuterium ion beams are used at Hispanos to produce neutrons by nuclear reactions. It is a very well-known method, and thus it's possible to deliver epithermal neutrons, fast neutrons, and thermal neutrons. So that could be all the infrastructure associated with the 3 megavolts tandem accelerator. I tried to summarize it so it doesn't take too long. And now let's move on to the rest of the CNA accelerators. This is the cyclotron. It was the second accelerator to be installed, and it can accelerate protons up to 18 MeV and deuterium up to 9 MeV. Its principle of operation is based on a constant magnetic field and an alternate electric field synchronized with the particle's trajectory frequency. The voltage is applied between 2 hollow disc-shaped sheet metal electrodes called discs inside a vacuum chamber. These discs are placed to face with a narrow gap between them, creating a cylindrical space within them for the particles to move. This animation excellently shows how it works. So particle basically defines a circle, and in each step it accelerates more. We could say that the main application is the production of radiopharmaceuticals, and that is production of radioisotopes for imaging modality in positron emission tomography, also known as PET. But it's also quite used in other applications, especially when the energy required for protons cannot be reached by the 3 megavolt tandem accelerator. Thus, here we can analyze materials, environmental samples, electronic devices, or even irradiation of biological samples. The next accelerator is the Cockcroft-Walton type 1 megavolt tandem accelerator. It's also called SARA. Its principle of operation is exactly the same as that of the 3 megavolt tandem accelerator, because it is a tandem accelerator, except that here the terminal voltage is achieved by a Cockcroft-Walton voltage multiplier, and the maximum achievable voltage is 1 megavolt. It is dedicated to accelerated mass spectroscopy and is currently the only AMS unit in operation in Spain. It is a nuclear technique for the detection of radionuclides, which are in very small amounts in nature. In particular, it is applied to those isotopes which are very difficult to detect using radiometric techniques. Of great environmental interest, this technique is able to identify one particle among 10 to the 15, which is incredibly sensitive. This is the ultra compact accelerator MICADAS, which stands for, as I said, mini radiocarbon dating system. It is an AMS system that operates as any other AMS system, but it is specifically designed for carbon-14 measurements, determining precisely the carbon-14 and carbon-12 ratio in a sample. The system is designed to measure concentration with high precision. So we are able to measure all the range of the possible archaeological and environmental applications. This way we can date any archaeological sample, piece of art, etc. For example, the CNA participates in projects to fight against illegal ivory trade, being this an important labor because of all the consequences of the illegal trade in this material. This is the gamma irradiator. It's a unit for irradiation with cobalt-60 gamma decay photons. We can irradiate large areas up to 140 by 140 square centimeters, and the rate is adjusted by changing the source target distance. This way, we complement the research in ion irradiation developed in the 3 megavolts tandem and cyclotron accelerators. This facility is available for use by the whole scientific community and companies interested in different fields of application. The laboratory setup has been done together with the company Alter Technology. The primary objective is to perform irradiation tests on materials and devices for aerospace application. But it's also used for applications in high energy physics, material science, biomedical, and agriculture. And finally, let me talk about the PET-CT human scanner. The principle is based on beta plus decay and electron-positron annihilation. A beta plus decay is a process in which a proton of the nucleus decays into a neutron, a neutrino, and a positron, which is the antiparticle of the electron. So when this occurs, this positron travels through the material of the medium and eventually comes to rest, annihilating with an electron of the medium, because as you know, matter and antimatter annihilate each other. And due to energy and momentum conservation, 2 photons of 511 keV are emitted in opposite directions, as showed here. So why am I telling you all this? Well, remember I said we could produce radiopharmaceuticals at the cyclotron? Well, so imagine we produce glucose with beta plus decay radioisotopes on it, and we inject those radioisotopes in our patient. The cancer cells need more energy to reproduce, so they will consume more glucose. So as I explained before, anti-parallel photons will be emitted, and since the body is surrounded by a set of detectors in cylindrical configuration, we can form an image of the tumor. So that's how a PET works. So there is an agreement with the University Hospital Virgen del Rocío to use and support the research facility in CNA. Presently, hospital patients of research interest are scanned at CNA 3 days per week, and for the remaining 2 days, the service provides the qualified staff for the human studies proposed by non-hospital scientific personnel. Moreover, the CT scanner is used for examination of large objects like pictures, sculptures, etc. Not only for human. So thank you very much for your attention.
Thank you, Adrián.
Oh, okay.
Go ahead, Giulio, if you want.
No, just thank you very much, Adrián, for this interesting talk.
You're welcome. Thank you.
Especially explaining us how CNA, all the facilities that are available at CNA. And it's very interesting for possible collaboration, future collaboration and project. So time for questions.
Exactly, time for questions. It's Remember, you can write them on the chat or just turning on your microphones. If there isn't anything, I can ask the first question, which would be, what are you doing in your thesis and what is your collaboration with IMB-CNM at the moment, Adrián?
Okay, I mainly work in the microbeam line. My thesis consists in the application of ion beam induced current technique to study semiconductor detectors. So my thesis consists of 3 projects, one of them in collaboration with the IEA, International Energy Atomic Agency, to study the effects on silicon, evolution, and the other 2 are in collaboration with the CNM. One of them is the characterization and development of silicon carbide detectors, made here at CNM. Well, we also carry that research in collaboration with the company Alter Technology. And the third one is the characterization of LGAT detectors, made also here at CNM. LGAT detectors are the main candidates to perform timing analysis in the next Large Hadron Collider upgrade. So that's mainly my work now.
Okay, thank you.
You're welcome. Thank you.
I have a question, if nobody else has a question. Adrián, what is the minimum energy, for example, that you can irradiate the detectors? I mean, for example, for protons, what would be the minimum that you can use, that you can reach the semiconductor, you know?
Yeah, it comes from this formula, but yeah, I would say the maximum voltage is 3 megavolts, but as you may suspect, if you put the maximum voltage, maybe you have stability problems, or I don't know. So
No, but I asked the minimum, not the maximum.
they just but the minimum it would be maybe, I don't know at which voltage this terminal voltage is stable. Maybe I can ask, but I guess if this is 0.5 volts, so you have 2, 5, so maybe 1 MeV. Yeah, I think we can have 1 MeV protons or less.
Okay, no, it's interesting to study, for example, the penetration of particles, low penetrating particles.
Yeah, the minimum actually would be, yes, to see how low the voltage can be for it to be stable and accelerate the particle at that voltage, but I've never asked which is that minimum voltage.
Okay, thank you. Any question? Any other question? Adrián's been here at CNM for 1 month now, and he will be here next week. If you have any question afterwards, you will be able to find him.
Yeah.
At least for next week or by email after that. So we are approaching the half an hour. Time for the last questions, if anybody has anything. Okay, Giulio, anything else you want to add?
No, from my side.
Okay. So thank you, Adrián. It was a very thorough summary of the CNA, so thank you very much for doing it for us.
Oh, thank you.
Thank you everyone for coming and well, for attending. As I said, you will be able to find Adrián next week at the center if you have anything else. And that's it for today. We will have another talk tomorrow about the AMIT, which is an association for egalitarian presence of female scientists in science. And that's it for today. Thank you very much and have a good day.
Thank you. Bye.
See you. Bye.